The constant and falling head tests are determinations of hydraulic conductivity, which deals with water flow through porous media. Geotechnical applications include dams, levees, cofferdams, retaining walls, sheet piling, subgrade drainage, and backfill drainage. In choosing a soil for a landfill liner or core of a dam, these tests are pertinent in finding the coefficient of permeability of the soil in question. The coefficient of permeability is an indicator of how permeable the soil is. The coefficient of permeability is defined as a physical property which indicates the ease with which water flows through soil. We determine it by two means which we will discuss, and that is constant head test and the falling head test. We will now discuss the differences in the constant head test and the falling head test. The falling head test is strictly for fine-grained soils such as clays, silts, clay sands, and silty sands. A small manometer is opened and flow is introduced into the sample. The changes in water level read from the manometer allow us to calculate the volume introduced over time. Then the flow rate can be calculated. Coarse-grained soils would introduce too much volume at once to obtain a decent reading with the falling head test method. Therefore, we use something called the constant head test method for coarse-grained materials. The constant head test applies a constant head to a sample over a certain amount of time, and a volume is measured from the outflow. A flow rate is easily calculated here, for volume and time are directly measured from the outlet. The constant head test does not work for fine-grained soils because too little flow would be available for measurement over time. We will now introduce the tools used for testing. First we have our fine-grained soil, which is our clay sand. Then we have our coarse-grained soil, which is a fine to medium sand. We have a funnel with a spigot on the end that reaches the whole length of the permeameter. We have a porous stone that fits on either side of the sample. We have our wing nuts to keep the permeameter tight and watertight as well. We have our wrench. We have a caliper to take inner diameter measurements of the permeameter as well as length of the specimen. We have our permeameters, or our vacuum seal grease to ensure water tightness, and our Vaseline, filter papers. We use the filter papers to cover the porous stone to keep it clean and free from aggregate. We have our tamper. We have our assembly for falling head and constant head. Here the tubes are used for constant head tests and attach into the top of the permeameter. That middle tube assembly is for the falling head test. We must first take all of our measurements before we begin assembling the permeameter. Measure the inner diameter of the tube. This will later be used to calculate the cross-sectional area of our sample. Next, measure the length of the tube. Measure the thickness of the two porous stones. The sample will be molded such that the length is the tube length minus 2 times the thickness of one porous stone. Thus the sample sits on either end of 2 porous stones that are flush with the end of the tube. Take and record all these measurements to the highest degree of accuracy the caliber is capable of. The inner diameter of the tube was measured to be 11.376 centimeters. The total length of the tube was measured to be 20.762 centimeters. The average thickness of the porous stones are 1.27 centimeters. Therefore, if molded correctly, our sample length will be 20.762 centimeters minus 2 times 1.27 centimeters, totaling to 18.223 centimeters for our sample length. The first and most crucial step in assembling the permeameter is greasing the gaskets. The vacuum seal grease prevents leaks from occurring during the test if applied properly. Grease all rubber gaskets on the bottom platen. Grease the outer diameter of the tube on the bottom end. Place the tube into the gasket and give the tube a slight turn so that the bottom end seats itself into the grease seal. Oftentimes applying a thin grease layer to the outside of the connection is necessary in preventing tiny leaks. Once the tube is on the platen, place the porous stone in the bottom. Filter paper should cover the stone and prevent any soil from contaminating the stone. Grease the outer diameter of the top tube if necessary. Grease the secondary top where the top of the tube will meet the gasket. Ensure the secondary top gasket has seated itself against the outer diameter of the tube. Apply another thin layer of grease if necessary. Next, use a funnel that has a hose or tube extending the length of the permeameter. Spoon or scoop the soil into the funnel. While placing lifts, move the funnel in a circular manner, working the funnel tip from the outside in. Once the lift has reached a uniform thickness of 0.6 of an inch, place another lift, again working from the outside in a circular manner. Place lifts in the same manner until the permeameter is full. Be sure that there is exactly 1.27 centimeters of tube length left at the top so that the porous stone can fit within the assembly. Cover the very last lift with filter paper and place the porous stone on top. Place the spring-assembled main top onto the permeameter. Slowly tighten the screws or wing nuts so that the top of the permeameter properly seats itself. In compacting a sample into the permeameter, we will use a premixed and moisturized fine-grained sample. This sample will be utilized during the falling head test. First, retrieve a representative moisture content sample of the specimen. Oven dry the sample at 110 degrees Celsius. The moisture content will later be used to calculate the dry density and finally the relative density of the compacted specimen. Next, weigh the permeameter with porous stones inside. This is essentially the weight of the mold. Grease and assemble the permeameter as necessary. Use a funnel to place 0.6 of an inch lifts in a circular uniform manner. Use a weight tamp to tamp the soil to the desired degree of compaction once the lift is placed. Oftentimes it will take multiple trials if a specific degree of compaction is specified. Use the same number of tamps at the same drop height for each lift. Drop the weight freely in a circular manner around the whole area of the lift. Compact each lift in the same fashion until the permeameter is full. Grease the top assembly and outer diameter of the tube and enclose the sample. Weigh the permeameter with the compacted sample inside. This is essentially the weight of the mold plus compacted wet soil. The next day, remove the moisture content tare from the oven. Weigh the dry soil and tabulate the moisture content. The moisture content was calculated to be 4.5% for our compacted sample. With the moisture content determination of the compacted sample, we can now calculate the relative density of our specimen. The first step is calculating the volume of the soil. Because the permeameter is a cylinder, we use the area of a circle times the length of the tube to obtain a total volume. Thus, the volume of the compacted soil is pi times the inner diameter of the tube squared divided by 4 times the sample length L. The volume is calculated in units of cubic feet. After unit conversion, the volume of our soil sample was calculated to be 0.0654 cubic feet. The moisture content of the specimen came to 4.5%. The compacted material is the same that we used in the standard Proctor test. Therefore, the max dry density was 123 pounds per cubic foot. The empty permeameter, i.e. mold, weighed 8.9565 pounds, while the compacted wet soil plus permeameter weighed 16.4085 pounds. So the weight of the compacted soil alone came to 7.452 pounds. With a known mass and volume, a wet density is readily calculated in units of pounds per cubic foot. Since we took a representative moisture content determination, we apply the dry density conversion to the wet density to obtain a dry density of 109 pounds per cubic foot. To calculate percent compaction or relative density, we compared the compacted dry density to the max lab value. Our specimen achieved 89% compaction of its standard Proctor. Again, this sample will be used strictly for the falling head test since it is fine-grained soil and was compacted. The simplest way to de-air and saturate the samples is applying a constant hydraulic head over a long period of time. Close the outlet and apply a constant hydraulic head to the sample. Try and remove any air voids trapped in the tube at the time of application. Also, one can open the bleed valve on top of the permeameter if the air pockets will not migrate up the tube. The bleed valve forces air and water out of the top of the permeameter. Once there is no change in hydraulic head with time and no air pockets are noticed, the sample is fully saturated and the test is ready to begin. We will first begin with the constant head test, which consists of coarse-grained material. Open the outlet valve and allow water to discharge. Keep adding water to the funnel until the flow is constant. Stop the flow. Set the funnel, i.e. hydraulic head, at the desired height for the first trial. Record the total head difference. Place a pan or beaker beneath the outlet so that all the discharge may be measured. While starting a timer, quickly open the outlet and allow water to flow out. During the specified duration of time, 30 seconds in our case, keep the hydraulic head constant by adding water to the funnel. After the time interval has passed, immediately stop the flow, record the exact time interval, transfer the liquid from the pan into a beaker or column to obtain a more accurate volume reading. Record the volume in units of milliliters. Readjust the funnel by 0.5 centimeters, i.e. increase the hydraulic head by 0.5 centimeters, and run the test again. Keep increasing the hydraulic head between trials by 0.5 centimeters until a linear relation between head and flow rate is realized. The falling head test will be run on the lighter sample shown. After connecting the small manometer hose inlet into the top of the permeameter, close the valve at the base of the manometer. Fill the manometer, release the valve, and fill the small funnel at the same time. This allows water to constantly flow through the manometer and into the sample. Once flow has stabilized and no air pockets exist in the manometer tube, close the valve at the base of the manometer. Adjust the water level so that a starting head value can be read off. Record the starting head value. While starting a timer at the same time, release the base valve below the manometer and introduce flow into the sample. Notice the meniscus in the small manometer drops. Allow the water level to drop to a measurable length, in our case the length of the meter stick. Record the amount of time it took for the water level to drop the length. Also record the head at the base of the manometer, H2. For the constant head test, Darcy's Law is the basis of theory behind calculating the coefficient of permeability, K. Darcy's Law is expressed in units of flow rate, length cubed per time. Q is equal to KIA, where Q is the flow rate, I is the hydraulic gradient, which is the hydraulic head, divided by the sample length, L. This makes this expression unitless. A is the cross-sectional area of the sample, which we know from inner diameter measurements of the tube. And finally, K is the coefficient of permeability in units of length per time. Darcy's Law is a simple means of calculating the coefficient of permeability unique to our test soil. Here's our constant head worksheet. The recorded laboratory data is in the first three columns of the table. Hydraulic head H in centimeters, volume V in milliliters, and time T in seconds. Hydraulic head is a length measurement from the top of the funnel to the bottom outlet on the permeameter. The volume is the measure of water that flows into the pan in a time increment t. The fourth column, flow rate, Q, can be directly calculated from the raw data. Conveniently, 1 milliliter is equal to 1 cubic centimeter. Thus, flow rate is calculated by dividing the volume V by time increment t. Assuming the dimensions of the sample do not change throughout the test, that is the cross-sectional area and length of the sample, the coefficient of permeability, K, can be calculated using Darcys Law. K is equal to Q over IA, where I changes with each trial because hydraulic head changes. K is a parameter unique to the soil, not hydraulic head or gradient. Therefore, K should look somewhat constant throughout trials. Before we discuss the plot, we must define the y-axis parameter. On the y is a quantity known as specific discharge or the Darcy velocity. It is often expressed as little q. Numerically, it is the flow rate, big Q, divided by the cross-sectional area of the sample. So it is the velocity of a fluid particle moving throughout the porous media. Now, by plotting specific discharge as a function of hydraulic gradient for our data, a linear line through the data set should be seen because the coefficient of permeability is constant and unique to the soil. The slope of this line, 0.1424 centimeters per second, is the average of the K values found on the previous page. The better the fit, the more accurate our results are. This plot and linear fit is a good means of verifying results of our test soil. Now we will move on to the theory of the falling head test. The coefficient of permeability in this case is calculated by an empirical relationship. K is equal to AL over big A T times the natural log of H0 over H1. Little a is defined as the cross-sectional area of the manometer. This is why we need to look up the inner diameter of the manometer in the owner's manual or find it by means of calibration. Little a times L yields the total volume introduced into the sample over a time interval t. Thus the units work out to be length per time. Recall that H0 was the hydraulic head before the base nozzle is opened, at time t equals 0. This is the hydraulic head at the very start of the test. H1 is the hydraulic head at the end of the test, time equals T1. So the hydraulic head falls from H0 to H1 over a time interval t. The inner diameter of our manometer was found to be 0.466 centimeters. Therefore, the area of the manometer equals 0.17055 square centimeters. Our hydraulic head dropped from 97 centimeters to 0 centimeters on the meter stick over 71 seconds. The distance from the bottom outlet on the permeameter to the 0 reading on the meter stick was found to be 82.5 centimeters. So by adding 82.5 centimeters to both hydraulic head readings, we obtain H0 and H1. By plugging in all the quantities into the falling head equation, with units remaining consistent, we calculate the coefficient of permeability for our fine-grained soil that was compacted to 89% of its standard Proctor value, 2.16 times 10 to the minus 3 centimeters per second. Recall the coarse-grained soil yielded a K value of 0.1424 centimeters per second. The difference in K values is 2 orders of magnitude. This is typical of a fine-grained versus coarse-grained soil. This concludes the test procedures and data reduction sections for the hydraulic conductivity laboratories.